Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
So let's start with the first topic, which is predictability in linear versus nonlinear systems. So the prototypical predictable linear system is a simple harmonic oscillator. A pendulum is another good example. What we're going to show you here is a mass oscillating at the end of a spring. So I'm going to use this same sketch later on when we talk about coupled oscillators. But for now, ignore this part. So ignore the fact that there could be a second spring. We'll show that later on. And just focus on having one spring and one mass, okay? So if you have one spring with a spring constant K1, and that basically tells you how strong the spring is, how hard it wants to spring things back if you move it away from equilibrium. So that's the spring constant K1, and here's the mass M1. And it could have an equilibrium position zeta 1. And so I don't have too much math in this talk, but I did want to show just a little bit of it for those of you that have taken some calculus. So the governing equation for a simple harmonic oscillator is linear. It's two time derivatives on the position. So if you take a time derivative of the one time derivative in the position, you get velocity. And if you take the time derivative of the velocity, you get acceleration. And acceleration multiplied by mass gives you a force. And so this term here is the acceleration in Newton's second law. Two time derivatives, that's the d squared dt squared, on the position zeta 1. And then over here, this omega 1 squared is the spring constant divided by the mass. You're dividing by the mass because Newton's second law has a mass in it. Force equals mass times acceleration. And so you just get this simple equation here where omega 1 squared is the strength of the spring K1 divided by the mass. And the solution for this, for those of you again that have had some calculus or trigonometry, is just a cosine function. So the equilibrium position zeta 1 is some amplitude A times a cosine of the frequency times time minus the phase. So the amplitude tells you how big the oscillation is, and the phase tells you something about the timing. And those are determined from initial conditions. And once the initial conditions are known, the motion is entirely predictable, and mathematically it just looks like this. So this and the next slide are going to be the worst ones for those of you that don't like seeing a lot of math. And then after that, there won't be too much, just pictures. But you know, it's a physics talk. I think we should have a little bit of math. So here's what a cosine looks like. It's nice and predictable. You start, let's just say, to make numbers up 5 centimeters this way, and then you swing down 5 centimeters that way, and back and forth. So here's a demonstration of it. So here's a very heavy mass at the end of a spring. So they told me to stand here for safety reasons. And you bring it down. Oh, I did that wrong. I was supposed to start it up. But it still works. So you have your spring constant here. If it was a stronger spring, then you get a faster oscillation. And there, obviously, there's your mass there. So this is a nice, predictable motion, simple harmonic oscillator. So some physical systems are nice and predictable like this. And I want to stress again that the equation here is linear. And so what we mean by that is that the variable you're interested in, the zeta 1, you only see it once. So you only see it once here, and you only see it once here. It's not multiplied by itself. Okay, so if, for instance, if this zeta 1 here was squared, then it wouldn't be a linear equation, and it would be a lot more difficult to solve and quite possibly a lot less predictable. All right, so in contrast to that linear predictable system, we're now going to talk about much less predictable nonlinear systems. So the prototypical nonlinear system is the Lorenz equation. So this is the second mathy slide. So the most famous system of nonlinear equations is the system written down by Ed Lorenz. So Ed Lorenz was a professor of meteorology at MIT. And in 1963, he wrote down these three equations. So the variables that you're interested in are capital X, capital Y, and capital Z. And they're all functions of time. And you have some constants here, this sigma, R, and B. And for certain values of these constants, this nonlinear system turns out to be incredibly chaotic and unpredictable. He was actually thinking when he wrote these systems down, of the weather. He had a very he wrote them down as a simplified model of the weather. I should mention, since I was a student at MIT, that I knew Ed Lorenz a little bit. I mean, I don't want to lie and say that we were best buddies or anything. He died a few years ago, but all of us grad students at MIT, we were in the same department as him, and so I saw him quite a bit. Interacted with him most often on hiking trips. So he was a really big hiker, and again, it wasn't just me and him going off to New Hampshire, but we'd have these retreats where 50 people would go to New Hampshire, and if you could hike fast enough, you could keep up with Ed Lorenz, and then a lot of the other people couldn't hike that fast, and so they were left behind, huffing and puffing, while this 80-year-old guy was rocketing through the mountains of New Hampshire. The other thing I was impressed by him is that there's a famous spot in New Hampshire, for those of you who know, it's called Tuckerman Ravine. So it's off Mount Washington, this really, really steep thing, and he said when he was young, he actually skied that. It's pretty deadly. So he skied Tuckerman Ravine, and he invented chaos theory. So he's a pretty impressive guy. Okay, so you have these nonlinear equations, and they're very chaotic, and we're going to demonstrate that by using the Malkus waterwheel. Okay, so there's another famous MIT guy named Willem Malkus, who is actually a student of Enrico Fermi's, and all the physicists here know what that means. Fermi was a very great physicist, and Malkus was one of his students. And Malkus realized that you could take Lorenz's equations and create an exact mechanical analog in the form of a water wheel. And the folks in the physics demo lab have generously built this Malkus-Lorenz water wheel for us. So if you want to write this down, if you're really interested in this, you can go to YouTube and type Lorenz-Malkus water wheel and see all kinds of animations of it, but we also have a real one built right here. And so this system here, this water wheel system here is an exact analog of the Lorenz equations. It has three governing constants, just like the Lorenz equations, and as you'll see, it's very unpredictable. So do I just press the, is that all I need to do? And then line it up, yeah. So one of the constants is how fast this water here is coming out. That's one constant governing the system. Then another constant is how many cups do you have, or equivalently, how widely spaced are they? And then the third constant is how big are the holes here for draining the water out. And so you can see pretty quickly that this system, in contrast to this system, is a lot less predictable, and that's because the governing equations are nonlinear. And I have to say, unfortunately, I'm using this famous example of nonlinear equations. I'm not really an expert on this system, so I'm not the very best person to explain all the subtleties here. But I think by eye you can see that it's much more erratic and harder to predict than that thing is. Okay, so getting back to the great Ed Lorenz. Ed Lorenz concluded that weather is not predictable beyond something like a 2-week window. That's not really hard and fast, exactly 2 weeks, but something like that. And so when you're predicting something as complicated as weather, you don't know, you can't measure every variable in that weather system with exact certainty. There's going to be small errors in it. And in a system like that, small errors begin to accumulate over time. and eventually you can't predict it anymore. So I don't know, this is kind of a hard concept to explain, but in a system like that, just imagine you look at it at a certain time and you don't know every variable precisely. There's small errors, and over a very long time, if you look at how the system evolves from this state versus one that's just a little bit different, which within the error bars, then you can get completely different motions 2 weeks later. And so that's why weather is inherently unpredictable past something like 2 weeks. And we know this from practical experience. If you go to weather.com, they'll give you a 10-day forecast, and we all know that the 10 days, you know, we don't trust that too much, out at 10 days. So another way this is sometimes discussed is the butterfly effect. So this is a colorful expression of Lorenz's equations. And sometimes people say, you know, does the flap of a butterfly's wings in Brazil set off a tornado in Texas? So the system is so sensitive that just this little motion here could have great consequences later on. Another thing that it leads to is something called data assimilation. So because weather is pretty unpredictable past a few weeks, the only way to really predict weather is you have to merge data and models in a process called data assimilation. And so what I mean by that is, if you want to predict the future, you have to use a model. The observations are not going to tell you by themselves what the weather is going to be like 2 weeks from now. And so you have to use a model that tells you this is what I think is going to happen in a few weeks. But you can't believe that model unless that model is forced to be near the observations right now, because the system is so sensitive. You've got to have all the clouds and hurricanes and whatever weather systems in exactly the right spot now if you're going to believe what it says a few days from now. So merging the data and models together is called data assimilation. And this field was actually started by a very great mathematician named John von Neumann. Some of you may have heard of. So he looked at the computers, the ENIAC they built in the 1940s, and he decided weather forecasting was a good problem to work on, and they started the field of weather forecasting. So nowadays, oceanographers also do data assimilation because flows in the ocean are similar to those in the atmosphere. And so if you have an unpredictable component of the oceanic flow and you want to predict it a few weeks in advance, you have to do this data assimilation. Okay, so fluid flows are also nonlinear and chaotic and unpredictable. And rather than show you equations, I'll show you some animations that illustrate that very well. So this is a type of fluid flow called Poiseuille flow with a high Reynolds number, which means the nonlinearities are strong compared to the turbulence, as compared to the friction, sorry. So Reynolds number measures the strength of nonlinearity relative to viscosity, or i.e. friction in a fluid. And so if that Reynolds number is quite large, then you can get turbulence. So I just showed you one animation of Poiseuille flow. I like this one even better. This is Rayleigh-Taylor instability. So that's really, really complicated, right? So if you look at something like that, you can just imagine it's a lot harder to understand that than it is to understand something like that. Okay, so fluid flows have all these different scales swirling around, complicated, turbulent, chaotic. These are the kind of words that we use to describe it. So fluid flows, including fluid flows in the atmosphere and ocean, are often inherently difficult to predict, and we have to use data assimilation to predict them well. Now, the next thing I just wanted to mention briefly is satellite altimetry data. This is especially appropriate for this audience because this is a talk about physics. And so one of the triumphs of modern oceanography is these satellite altimeters. So the word altimeter gives you a clue what we're talking about. It's measuring height. Okay, so these satellites can orbit the Earth at something like, well, it says there 1,336 kilometers. They send microwaves down to the Earth's surface, and then they measure the return time. So if the sea level is higher than average, then it's going to take less time for that microwave signal to return. And they can measure departures from average sea level at an accuracy, it's unbelievable, at 4 to 5 centimeters. So imagine this thing is up in space about 900 miles, and it's measuring the accuracy of the sea surface height to levels something like this. So it's a real triumph of modern oceanography, but also modern physics. So obviously there's quite a lot of physics goes behind that. In fact, in order to measure, I don't really understand the details of this part of it very well, but I find it impressive. In order to measure heights that accurate, they have to do Einstein's general relativistic corrections. You can't measure things that accurately without doing general relativity, which is hard stuff. So here's an animation of what the satellite altimeter data looks like. All right, so the satellite altimeter measures sea surface height, and so any ocean phenomena that has a sea surface height signature can be studied with the altimeter. That means El Nino and also mesoscale eddies. So all these things here are what we call mesoscale eddies, and what they are is essentially the ocean equivalent of atmospheric weather systems. So just like the atmosphere has this strong current called the jet stream, and that jet stream spawns off these spinning high and low pressure systems, the ocean does as well. Except in the ocean, they're much smaller, so there's many more of them than you see in the atmosphere. So in the atmosphere, a weather system could cover a whole continent, but in the ocean, because these eddies are smaller, you see a lot more of them. So this is an animation of the sea surface height as seen by the altimeter, and this animation was given to me by the head of the whole project. So he came here to Michigan several months ago and said, oh, here's a nice movie you might want to show people, and here it is. So this is the anomalous sea surface heights in the ocean. This does not include the tides. So this has been, as we call it, de-tided, because if you had the tides in there, you'd only see the tides. So you have to get rid of the tides to see other things. And that, what you're just seeing right there, that's El Nino. Okay, so this big pulse traveling across the equatorial Pacific, that's the El Nino signal. So tides is one of my specialties, so I can tell you that for a lot of oceanographers, they view tides as kind of a nuisance. But you can't do the rest of physical oceanography with this data unless you accurately remove the tides. If you didn't remove the tides, all you would see there is the tides. They would bury everything else. Okay, so tides are both signal and noise in this game. If you're interested in tides, you use the satellite to look at the tides. If, like many oceanographers, you view the tides as a nuisance, you must subtract them out before you can see the rest of the phenomena in the ocean. And again, you can see just by looking at this stuff is not easy to predict, right? If you want to predict these motions, if you freeze time there and you want to see what the motions are like a week or two later, you can probably do it. But if you freeze time at a certain spot and run your model for years and years and years, by the time it's gone for years and years out, you're not going to believe your results anymore. Okay. So that's a demonstration of that technique. And now what I want to do is talk about numerical modeling of oceanic motions. This is another really important revolution that's happened in modern oceanography. There's the satellite data and other types of data. There's these really wonderful autonomous floats called Argo floats that float around the ocean and come back to the surface and radio information. So modern technology has really done marvelous things for our understanding of the ocean, but I can't show you everything. So I've showed you the satellite altimeter, and now I'm going to talk about numerical modeling. So if you want to use a big computer to model flows in the ocean, you have to take the equations for conservation of momentum, mass, and heat, and discretize them on a numerical grid. So for instance, the Navy folks that I work with are running right now the biggest ocean model in the world, the biggest global oceanic model. So the biggest model, what we can do is, if here's the Earth and this is the east-west direction, we have 9,000 grid points in this direction. And we have 6,600 grid points in this direction, the north-south direction. And then at each horizontal location, we can have 32 layers in the, that you have the surface of the ocean down to the depths. So if you just do that in your head, 9,000 times 6,600 times 32, you get a really big number. And so basically the number of grid points that you can simulate depends on how large your computer is. Okay, so the models I'm about to show you cannot be run on a laptop. So they take the equations for, so some of these equations, I just wanted to say a little more about that. So the conservation of momentum, that's basically just Newton's second law. You have various forces acting on fluid parcels, and those forces cause acceleration. And then conservation of mass, so for instance, if currents are going like this, then they're going to cause sea level to go up, and if currents are going like this, they're going to cause sea level to go down, things like that. So we need to put these on really huge computers. So most, if not all, of the largest ocean simulations run today, they utilize what's called parallel programming, and they're run on supercomputers. So the idea, so it's kind of surprising. These big supercomputers I'm going to show you in a minute, the individual processors in these computers are not necessarily any faster than what you have in your laptop, but there's 100,000 of them. Okay, so here's a supercomputing center at the University of Texas. So the Texas Advanced Computing Center, and I just like to show this. So this is what these supercomputers look like. Okay, so this is a supercomputer center at the University of Texas. It has 63,000 processors. And I like to show this particular one for two reasons. One is that my postdoc works on this. In fact, he proudly told me a few weeks ago that he crashed that whole system. The people at the other end at Texas weren't so happy with him, but it's kind of a cool achievement, you know, to bring down a system like that. And the other thing is that I used to work there. So when I was at University of Texas, between my postdoc and my first assistant professor position, I worked 2 floors above that in the same building. It's pretty impressive when you go in there. When you have 63,000 processors, it's unbelievably loud. And also they generate so much heat that they have to run a lot of chilled water through air conditioning systems to keep it cool. In fact, I kind of wondered, why did they put a huge supercomputer in Texas? But I think it generates so much heat, it really doesn't matter where you put it. And they're pretty used to air conditioning in Texas. So we use those kinds of machines in our research. All right. So there we go. So the next thing I wanted to talk about a little bit is we've talked about there's some motions in physical science that are fairly predictable, like the first demo. There's some that are less predictable, like the second demo. And the ocean has motions on all kinds of space and time scales. There's high frequency stuff, there's low frequency stuff, there's motion on really small scales like swirling, breaking waves, and then there's motion on planetary scales. So there's all kinds of motions in the ocean, and some of them are more predictable than others. So this will be, I'm just kind of curious how this will go. So I'll try one interactive thing. So what type of motion in the ocean is famously predictable? I'll give you a hint. So tides, exactly. So tides are pretty predictable. The moon is there, the sun is there, the orbits are known, and tides are famously predictable. So they're the prototypical predictable motion in the ocean. But the ocean's driven by a lot of things. There's the gravity of the moon and sun gives you the tides. It's actually, to be precise, it's the differential gravity across the finite size of the Earth. I could explain that later if anyone's interested. But the atmosphere also drives the ocean. And the thing is, the winds themselves are unpredictable. And so if you've got these unpredictable winds, i.e. weather, driving the ocean, that means that the wind-driven circulation of the ocean, especially those little unstable eddies that develop off the currents, those are a lot harder to predict. And wind-driven surface waves, the ones that surfers like to surf, and I'll show a video of that at the very end, they're fairly predictable once they're generated, but when they start breaking, of course, that's a different story. And also, it's hard to predict the winds that generate them in the first place. So what I want to do now is look at some animations of oceanic motions for a little bit. So let's start with this one. And so this is going to show you sea level height. We haven't started it yet. Here's your scale for sea surface height, and here's the timing. So when you see this, I think you're going to guess what it is. So what happened right after Christmas in 2004 in the Indian Ocean? Yeah, this is a tsunami. So it's kind of interesting to think about the predictability of this. Earthquakes are not very predictable, but once you have an earthquake, this thing had the seafloor deforming by something like, I think it was almost 50 feet, something like that. I should know since I put it in this model, but it was many years ago. And you put that as an initial bump in your model, and then it just flows out. So it's hard to predict the earthquake, but once the earthquake happens and you know the initial condition, after that it's actually pretty straightforward. It just propagates around as a linear wave. You can see that by the first and second day, the wave was actually all seen all around the world, and tide gauges all around the world actually did see the tsunami cruise through for a little bit. Okay, so that's a tsunami. If you can just imagine, if you were an oceanographer in early 2005 and you had a model that could do that tsunami, you were pretty much pressed into service to do that. But I just spent a few weeks on it, and it was really just kind of a hobby. Here's what the tides look like. This is more one of my specialties. So this is a model of the M2 tides. So M2 stands for moon twice daily. So it's the principal lunar semi-diurnal tide, has a period of 12 hours and 25 minutes. And first look at the one on the left. The scale is here, so on the left you see it's in meters. So low tides are maybe half a meter or a meter low, so that's maybe 3 feet low. And then high tides are in the red. So if you look at a spot like this, the Gulf of Panama, so here we have a high tide, and then 6 hours later we have a low tide coming in. There we go. So that's what the tide looks like in sea surface height as it propagates around the world. You'll notice that many of the places of large tides are in coastal areas like here and the Sea of Okhotsk and here in Alaska. So what we think is happening is this, that the waves travel with a simple formula, the square root of gravity, which is 9.8 meters per second squared, times the depth, h. And if you take an average depth in the ocean of 4,000 meters, you'll find that they travel at the speed of 200 meters a second, which is basically about the same speed as a jetliner. Okay, so they're traveling about as fast as a jet, which is why it's hard to outrun a tide or a tsunami if you're on the beach, or a tsunami. They're traveling that fast. So then if you take the 200 meters a second and you multiply by the forcing period of 12 hours, you can look at how much distance they'll cover in one forcing period. And the kind of numbers you'll get are comparable to the sizes of the ocean basins. So basically the tides travel across the whole ocean basin about the same period as the forcing. So it ends up being like pushing someone on a swing. So the tidal forcing period is about 12 hours, and it takes about 12 hours to cross the basin. And so if you look at the globally average response of the tides versus the forcing, you'll find that they're amplified by a factor of about 3. And so we think that they're what's called resonant, a resonant phenomenon. So we think that the open ocean tides are resonant. It's not a super strong resonance, but we think they are resonant. And then in coastal areas, certain coastal areas, if they have exactly the right depth and shape, then what will happen is, again, the wave will travel down the bay and come back at just about the right time to be like pushing someone on a swing. And so you get a secondary resonance there. So some of you probably know, where's the highest tides in the world? Bay of Fundy, yeah. So the highest tides in the world are in the Bay of Fundy, which aren't shown here. They're in eastern Canada, about here. And an interesting story about that is that There's another place in Canada called Hudson Strait, which is much more remote, but it turns out to have tides that are basically as large as the ones in the Bay of Fundy. And that presented a problem for the Canadian Hydrographic Service because there's lots of tourist dollars in New Brunswick and Nova Scotia associated with the highest tides in the world. So they said, well, let's just call it a tie. So there's 2 different places in Canada that have the highest tides in the world. All right, so, and you'll see a bit more about that in a second. Now the other thing I wanted to show is, so on the right, you might notice we're going from meters to decimeters, so you're multiplying the scale by 10. And so on the right is what we call internal tides. So what does that mean? This is pretty neat. All right, when you have tidal elevations, you also have tidal currents. And if those tidal currents flow over a big topographic bump, like say the island of Hawaii, so the ocean, you know, Hawaii is just a really big bump, okay? So if you flow over that bump, you're going to cause vertical motions, all right? Now what does that imply? Well, the ocean is stratified, so you have light water over heavy water. So imagine you idealize the ocean as having 2 layers, a light layer and a heavy layer and an interface in between. So if you flow over the bump and you cause vertical motions, that interface is going to go up and down. And it's going to go up and down at tidal frequencies, and that's what you're seeing here. Okay, so these are motions that are very large in the vertical direction. In fact, near Hawaii, they can be 300 feet high. So they had this article in a Hawaii paper, 300-foot high waves. But they're not 300-foot high waves at the surface. They're 300-foot high waves on a density surface, maybe a few thousand feet below the surface. So if you're a few thousand feet below the surface and you put yourself on this density surface and you moved up and down with that, you could be moving up and down by a few hundred feet at tidal frequencies, and that's called an internal tide. And so these internal tides have very short horizontal scales compared to this, as you can see, but much larger vertical scales. And they're very interesting to oceanographers because just like waves on the surface, these internal tides end up breaking. So they cause a lot of turbulence within the ocean, not at the surface, but way down underneath. And so if you're interested in turbulent mixing, all that turbulent stirring and stuff underneath the ocean, as a lot of oceanographers are, then you're interested in these internal tides because those waves on the interfaces, they turn over and break just like waves at the surface do. So this movie here was made by myself, and another movie was made by the person I was collaborating with at the time. And so this is just kind of an interesting lesson. I put the tides in this code, and then I made that movie. And then he started working with me, and he made a much nicer movie. And so people always show that movie now. Okay, so how did he make a better movie? Well, he chose an aesthetically more pleasing color bar scale. And he also chose to start it from rest. So in mine, I started it from once it was already spun up, but he started it from rest. So you're going to see these waves developing. So here you go. So again, what the reds and the blues mean are these are waves of tidal frequency going up and down, but they're not at the sea surface. They're a few thousand feet below the surface. So these are waves. They're called internal waves because they're internal to the ocean. They're not at the surface. So these internal waves, again, they break just like waves at the surface do, and they stir things up and mix things, and oceanographers are really interested in that. And when we did these simulations, Harper Simmons and myself, they were the first ever global simulations of internal waves in the ocean. No one had done that before. These happen to, in particular, be internal tides, although winds can also cause these kind of waves. So this remains one of my, as we say in science, most highly cited papers. Other people were pretty excited about it. Okay, so then I also wanted to quickly show, so I've shown tsunamis and tides, but what about the atmospherically forced part of oceanic motions? So let's take a look at a movie on that. So what I'm showing here is a model called POP. So one of the first big ocean models was called MOM, which was a modular ocean model. So then the competitors made a model and they called it POP. And that stands for Parallel Ocean Program Model. So this is the model that is run by the Department of Energy. So as you may know, the Department of Energy tends to have some of the largest computers in the country. So they run it, this is the ocean model they run on their large computers. And so this thing has no tsunamis and no tides in it, but it does have the motions in the ocean driven by the atmosphere. So, except it doesn't have, it's very complicated, it doesn't have the waves that break on a beach, which are also driven by the atmosphere, because those features are too small. Okay, so this grid here is thousands of grid points wide, similar to the models I work on with the Navy. But that's not enough resolution to resolve the kind of waves that break on a beach. So those kind of motions are not in this model. But instead, you have what we call the general circulation, the large-scale flows in the ocean. And so how does the atmosphere force the ocean? So first of all, density, the ocean is stratified. You have light water over heavy water. And the density is controlled by two things, temperature and salinity. So cold water is dense, so it's going to settle down to deeper waters. And salty water is dense, so it's going to settle down to deeper waters. The salinity of the ocean is controlled by evaporation and rainfall, which are both controlled by the atmosphere. If you have rainfall, you're going to make it fresher and less dense. And if you have hot weather, you're going to evaporate a lot and make it saltier. So that buoyancy forcing, we call it, is part of the forcing here. So these colors here are temperatures. So this is sea surface temperature, warm in the tropics, cold in the poles, and this is the seasonal migration. So now it's getting into northern winter, so the warm temperatures are climbing down, which means it's summer down here. And now it's getting into southern winter, so the warm temperatures are moving back towards the equator. And that's the same as northern, I hope I got that right. It's southern winter is like northern summer and vice versa. So that's the temperatures moving up and down. So the atmosphere forces the buoyancy of the ocean, the density, through the heat fluxes which control temperature and the evaporation and precipitation which control the salt content or salt concentrations. But of course, the other big thing that happens is that the wind blows over the ocean. And so when the wind blows over the ocean, it makes surface gravity waves, the ones that surfers enjoy, which we cannot resolve in this model. But what it also does is it drives these large-scale currents, which we call the general circulation. And so the general circulation, the most important features there are called western boundary currents. So I always find this kind of amusing. So as Americans, we think of this as the East Coast, right? But if you're an oceanographer, this right here is the Western Atlantic, okay? So if you have an ocean-centered view of things, it all switches. So it turns out that the strongest currents in the ocean are always on the western side. So here, the western North Atlantic, you have the famous Gulf Stream. And then in the western South Atlantic, you have the Brazil-Malvinas current. And western South Pacific, you have what's called, confusingly, the East Australian current, because it's off the east coast of Australia. So that's where they kind of got their signals a little cross. Then you have the Kuroshio coming off Japan. And then this is called the Agulhas current here. And then there's a current that goes all the way around the oceans here, which is known as the ACC, Antarctic Circumpolar Current. So you have all these currents in the ocean, and these big, strong currents, notice they're generating these little spinning eddies. And so these are the ocean equivalent of atmospheric weather systems. Remember, in the Altimeter movie, you also saw these little spinning things, and here's a view of them in a numerical model, these spinning eddies. So those are like the ocean equivalent of atmospheric weather systems. So here's the last animation I'll show. This is the same Department of Energy model, but it's just a little bit different view of it. Notice how it's run on a supercomputer in Japan called the Earth Simulator. And so this shows not only the sea surface temperature, but also sea surface height. Okay, so these little spinning eddies have signatures in sea surface height. So some of them are high sea surface height and some of them are low. So it might be a little bit hard to tell from this, but these things here are inherently hard to predict over long time scales. So the tides are like our first demo. They're easier to predict, and then these eddies are like this demo. They're a little harder to predict, actually a lot harder to predict. So if you want to predict those ocean eddies on long time scales, you have to do it with a model that includes data assimilation, where you're forcing it to be near the data at this time, and then you trust what it says a few weeks from now. And in case you're curious, why is the Navy interested in ocean forecasting? It's basically because if you want to track submarines, then the acoustic signals are very sensitive functions of all this activity that's going on in the ocean, the tides and everything else. So all that stuff that's going on affects acoustic tracking of subs. That's why they're interested in it. And so if we think the tides are resonant, we might want to model the global ocean tides like this. So we think of the open ocean, the big open ocean, as a big mass with a big spring. And then the coastal tides we think of as a little mass with a little spring, and they're connected together. The coastal ocean and deep ocean are connected together. So without getting into the details of the math, I'll just show you the punchline. If you have a big spring connected to a little spring, and if they're both near resonant, then it turns out that the little spring is generally going to have larger amplitudes. So what we're showing here is the amplitude of the shelf, so that's the little one. So the coastal ocean is often described as a continental shelf because it's like a shelf that drops off into the deep ocean. So this is the shelf amplitudes as a function of the forcing period. And so if the forcing period is close to the resonant period of the shelf, then you're going to get a large response. Okay, so that's not too surprising. But the interesting thing is looking at the open ocean. So what this thing predicts is that if you have a shelf attached, so that's this blue curve here, the open ocean will have a resonance. If you then detach the shelf, even if it's very small, the response of the ocean increases by a factor of 2. So essentially what that means is even if you have a very small spring and mass connected to a much larger one, if they're both near resonance, the little guy actually affects the big guy by quite a bit. And such that if you detach it, the motion of the big shelf, big ocean can be a lot larger. So Monica will now show a demo. This is our last physical demo of the day of this of a coupled spring system.
We have a large mass attached to a spring, and then to that mass we then have a second mass that's much smaller attached with another spring. And we have this entire system attached to an exciter here that will excite the system at a specific frequency, and then we'll see how it reacts. This little ball up here is going to show you about how much we're exciting the system, and then you'll be able to see the response within this here. So to start out, I'm going to show below resonance. You're going to see that this is moving very minimal amounts, and you'll see that they are, the response of this is pretty slow, but the response of this is going about twice as fast. If I go above resonance, much higher, then you'll see this is exciting very quickly, but you'll see the response of this is still about what it just was. When you're near resonance, you're going to see that this spring is going to be reacting much more than this spring here. And so much that if this post wasn't here to keep it restricted, this thing would be flying all over the place. But you'll see that just a little excitation at that resonant frequency gives a large response when you've hit that specific point.
Great. So this is the Bay of Fundy, right? So the little spring, the Bay of Fundy, can have much larger motions, and it was a little hard for us to figure out how to show it there, but it also can affect the motions of the larger mass. And so here what it's saying is that if you have the Bay of Fundy attached, your tides in the open ocean are here, but if you get rid of the Bay of Fundy with certain important parameter values that are relevant to the ocean, then you can get a much larger response in the ocean. So to show that a little bit more, here's a plot of the amplitudes of the M2 tide. Remember, again, that stands for moon twice daily, principal lunar semidiurnal tide. And these are the amplitude of the tides. Here is in a model that comes from those satellite altimeters that I talked about earlier. So here's the large tides in the Bay of Fundy right there, and here's the large tides in the Hudson Strait. Remember, they're a statistical tie. Both the largest ones are in Canada. And so if you have really large tides in places like that, that means the tidal amplitude goes up by more than a meter and then down by more than a meter just for this frequency. There's more frequencies in the ocean. So that's from the satellite, and here's from my model. So if you look, you can see that that model that I showed earlier of the big blobs traveling around, that's my model. And you can see by eye that we've tuned the model enough that there's pretty good agreement between the computer simulation and the real data. So we tend to trust what the model tells us. So now what we're doing here is we're testing some of the concepts of the coupled oscillators. So we run a global model. We look at the tidal amplitude in the Hudson Strait region. There's the Bay of Fundy. There's the Hudson Strait, statistical tie for highest tides in the world. You have those big tides, just like you see in observations. And then what you do, you can barely see it here, but we've cut this little line here, right? And so why do we do that? We basically sliced out Hudson Strait. And so what this model of the coupled springs predicts that the open ocean tide should get a lot bigger when you get rid of the small guy. And so here what we're doing is getting rid of the small guy. We're slicing it out, and then look at the amplitude of the tide in the Labrador Sea. See how it jumps from here to much redder colors. That means it's gotten a lot larger. In fact, if you then difference them, if you take a difference of the tidal amplitudes in the case where you block it out artificially versus where it's there, you see that it affects the tides not only in the Atlantic but as far away as the Indian Ocean. So the most famous living oceanographer is named Walter Munk. The first thing he did as an oceanographer is he actually was involved in predicting the surf for D-Day. It's a fairly high pressure assignment. He's in his 90s now, but when he saw these results, he said, oh wow, geophysical warfare. You can make the tides bigger somewhere else by blocking off certain bays. So I thought that was interesting. So it also has implications for ice age tides. So, you know, we want to understand tides for their own sake, and we're trying to show the coastal tides affect the deep ocean tides. But there's some motivation for this in the geological record. So during the ice age, there was all this ice over land, right? So Michigan was under a few miles of ice, you've probably heard. So, well, where did all that water come from? It came from the ocean. So sea level during the ice ages was as much as 400 feet lower than it is today. And so if sea level was much lower, what does that mean for places like the Bay of Fundy? They weren't even there. Okay, the sea level was so low that such of these places were gone. So during the ice age, that's like going around and blocking out all these bays, just taking them out of the equation. And so all the work we've done so far would predict that the tides of the ice age would have been larger. And you can see that here. So if you look at the tides in the Labrador Sea here, this is an actual simulation of the tides of 45,000 years ago. And you have much larger tides in the North Atlantic, especially the Labrador Sea right there, than you do in the present day. So this was actually what came first. We first wrote a few papers on, gee, the tides of the ice age seem to have been a lot larger. And then we tried to come up with a theory for it, and we did all that stuff with the springs that I showed you. So then another thing I just want to show real quick, because it involves students. So I can explain later if people want in the Q&A, but tides are not just at twice per day. There's also frequencies at once per day. They're called diurnal tides. And it turns out the same phenomena happens with diurnal tides. So the largest diurnal tides are in the Sea of Okhotsk, up here in the Pacific, right there. And if you block those out, you have a global change in the diurnal tides. And so Aaron Skiba and Libo Zheng, so Libo Zheng's actually a physics major here at U of M. He's an undergrad. And Aaron Skiba is an aerospace engineer. And so this project was started by these two students who worked with me at Florida State. And then when I moved here, Aaron and Libo, undergraduates here at Michigan, finished the project, and we're going to send it in soon. Okay, so the last few things I want to talk about, another line of research I'm doing, and that's with the Navy Ocean Modeling team. So again, they're interested in modeling the ocean for operational purposes. They're interested in acoustic tracking and other U.S. Navy fleet operation type things. But they also, by the way, just as an aside, were called in, as you can imagine, when the Gulf of Mexico oil spill happened. People like them were called to predict where the oil is going to go. So I've been working with them. They're the largest users of Department of Defense computer resources. So all the Department of Defense people, these are the guys that chew up the most computer resources and make everyone else mad. That you're using the whole computer, and especially the storage. It's not just the computer cycles, but you got to store all the results is another problem. So as I mentioned, I work with these Navy folks. They use a model called HICOM, Hybrid Coordinate Ocean Model. That doesn't really matter what all that means unless you're really interested later. The Naval Research Lab and the Naval Oceanographic Command, NAVOceano, they're in Mississippi, and they run HICOM as a global operational or ocean forecasting model. They have to use data assimilation because a lot of the motions, the tides are an exception, but the other motions are chaotic, so you can't predict it over long time scales unless you put the data in there. And the thing is that forecasting models like other global ocean models didn't have the tides until recently. So I was showing you global models of tides and global models of the atmospherically driven part. Until recently, those were done as separate endeavors. There's a lot of technical reasons that it's hard to stick them together. So I worked with them for several years, and we published the first simulations where we had the atmospheric forcing and the tides at the same time or concurrently. So that's a new thing that we're playing around with now. And I'll show a few results that we have recently. They're not even published yet that build upon that. So Jay Shriver, who's a scientist at Naval Research Lab, is working with myself and these other folks. We're doing a global comparison of the internal tide amplitudes at the sea surface in our model versus the satellite measurements. So this is a little bit complicated, but so the internal tide has small horizontal scales, and it's really large at the way underneath the surface. But it has a small but detectable signal at the sea surface. It can be detected by the satellite measurements. But in order to separate it from the much larger blobs that you saw, if you want to see the small scales, you have to do what's called a high pass. And so if you do a high pass, and you basically filter out the large motions and only the small ones are left. And so the satellite altimeter has these tracks, so you can see the trackiness. The data is along certain tracks. If you look closely, you can see the tracks there, and then the little white space in between the tracks. And if you look at the data along the tracks and you do a high pass, this is what the satellite data looks like. So the sea surface signature of these huge waves underneath is about 1 centimeter or so. And if you look in the model, this is what you see. And you can see in general these patterns are pretty similar. So NASA is planning a new generation satellite altimeter where they're going to measure sea surface height with a different technique called interferometry. And they're going to measure the sea surface height at much higher resolution than we can do at present. And what that means is that the tides, which are always a source of interest yet noise at the same time, are going to be important at the small scales. So for this instrument to work over the ocean, they're going to have to map and remove tides at small scales. And so since we have the best model for this right now, I get called to all these NASA planning meetings basically to show these kinds of pictures. And then the last thing I'll show before a surfing video is, I'll end with a surfing video, but I want to show one more scientific thing. And these next few slides were actually called for by the NASA scientists. So they basically said, okay, you've got this model. What we want you to do is we want to calculate what's called a wave number spectrum. And so a wave number spectrum, it tells you how much energy there is in certain scales as a function of scale. So this will just take a minute or two to go through. So here's what the internal tide looks like at the surface. And we look at all these various boxes here, 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 and so on. And you can see in some of these boxes, like this one, there isn't much of a tidal signal, whereas this place near Hawaii, there is a big tidal signal. So one thing you can do with this model that's very hard to do with the satellite altimeter data is before you do the wave number spectrum, you can separate it into temporal frequencies. So you can look at the really high frequency stuff like tides versus the other stuff. And so if you look in this box here, for instance, it's probably hard to see all the colors, but the black line, which is pretty much on top of the blue line, is the total sea surface height. The blue line is the low frequency sea surface height, and the red line is the tide. So in this region, the spectrum, so this is the how much energy there is as a function of wave number, which is inverse wave length, inverse length scale. So here's how much energy you have as a function of length scale in the tides, and here's how much energy you have in the low frequencies. So what that means is, if you're in an oceanographer, you're looking in this region, the tides are not going to dominate your signal. So if you don't want the tides to dominate your signal, you want to look in this region. But if you look in this region near Hawaii, it's the opposite story. So the tides in red are much larger than the low frequency stuff in blue. So if tides are your signal, you want to go here, and if tides are your noise, you want to go here, and NASA wants to understand which regions have which properties. So the satellite is planned to launch in 2019, but as a prototype, they're going to launch an aircraft campaign called AirSWAT, and they're going to do this in the next year or so. One site is in the Mediterranean right here. Another site is off of California. So they asked us to do the same exercise, and it turns out for this first exercise, they want to go to places where the tides are not dominant. And so we were able to do these calculations and say, well, if you trust our model, it's telling you that the tides will not be dominant at those places. The other motions that you're interested in will dominate. So this actually helped them plan their air campaign, which will go out about next year. Okay, so I've talked a bit about oceanography in general and some of my research, and I'll end with this. So we've emphasized the wind-driven general circulation, the Gulf Stream and things like that, and the tides. We showed a little bit of tsunamis. But obviously there's other types of motion in the ocean, and these ones require different models than the ones I work with. So you're going to see surfers surfing on waves, incredible waves, and these waves are much too small in horizontal scale to be resolved by the kinds of models I work with. But it's just a fun video to end with.
I realize that, you know, this is the day and this is the time to go for it.
Check it out. On the far outside, we've got another set coming. Let's see. Yes, it is critical, and it is absolutely huge.
You know, I was in deep enough water, I came up screaming at Brad, that thing was insane. I think I just got a huge score, man. That wave was incredible. This is the best wave I've ever surfed. It was just like so much adrenaline. Like I was freaking.
But I'm looking over at kind of all the other boats in the crowd, and they're all going, yeah, like this, and I'm going, he really must have done something sick, you know? It was unreal.
Congratulations to our winner, Garrett McNamara, and to Mike Parsons for what seemed to be the wave of the century. And all our competitors, congratulations for surviving one of the most...
So that was 64 feet. Thanks a lot.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment. the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.